the second part of the video introduction to Module 6. In this video, we will talk about the chi-square goodness of fit test for a single categorical variable. Now, in Chapter 6, we've already seen how when we have a single categorical variable, we can do a hypothesis test about the proportion that falls into a single category of that categorical variable. We test hypotheses about a single proportion P, and we'd use a Z test statistic to do that, as long as our sample sizes are large enough. But what if we want to test some hypotheses about proportions for several different categories all at once instead of just one category? Instead of a single proportion, now we'll be interested in hypotheses about multiple proportions. For instance, we are looking at Reese's Pieces. Their null hypothesis might be that there are 25% yellow, 25% brown, and 50% of all Reese's Pieces that are orange. The alternative hypothesis in this situation is going to be that at least one of those hypothesized proportions is incorrect. Why won't we be able to use the familiar looking formula, the sample statistic minus the null hypothesized value divided by the standard error to get a standardized test statistic? Well, we've got more than one sample statistic. We have sample proportions in lots of different categories, and we have more than one hypothesized value. We've got hypothesized proportion for each of the different categories. So we can't work with this. Instead, we're going to need something that's a little more complicated. So the way we're going to work with a chi-square test in this situation is going to be by thinking about if the null hypothesis is true, what counts would we expect to see? Not what proportions, but what would be the counts that we'd expect to see, the frequencies in each category. So coming back to our hypothesized values here, what we'd expect is that if 0.25 is the proportion of all Reese's Pieces that are yellow, then the proportion of the sample would be somewhere around 0.25. So the way that we are going to find the expected count is by taking the sample size, 24, and multiplying it by the proportion in that we hypothesize for each category. So we'd expect sample size 24 times 0.25 is our hypothesized proportion. We'd expect 6 yellow. We'd expect, since the hypothesized proportion of 0.25 is for the brown, we'd expect 24 times 0.25 gives us 6 brown. And since we hypothesize that half of all Reese's Pieces are orange, we'd expect that approximately half of our sample, so 24 times 0.5 would be expecting 12 orange in our sample. So just kind of thinking about, well, how can we think about what we'd expect to see? So in general, the expected count in category I is going to be our sample size n times p sub I, the hypothesized proportion for category I. We'll use those expected counts to calculate something called a chi-square test statistic. What the chi-square test statistic is going to do is compare all of the sample statistics to their hypothesized values, and it's going to do this by comparing the observed counts and the expected counts in each category. Now this chi-square test statistic looks a little complicated. What we do is for each category, we take the observed number in that category and subtract the number we would expect to see if the null hypothesis is true. Then we square that quantity and we divide it by how many we would have expected to see. Once we do this entire piece for each of the categories, the sigma notation here is telling us to add them all up, and that's going to give us our test statistic. And again, this is known as a chi-square test statistic, It's used for comparing the observed counts of categorical variable to the counts that we'd expect to see if the null hypothesis were in fact true. If we get a large value of the test statistic, what that's going to indicate to us is that the counts are far away from what we would expect to see if the null hypothesis is true. So the larger this chi-square test statistic is, the stronger the evidence is going to be against the null hypothesis. This is called a chi-square test statistic because when we use it, we need to use a distribution called the chi-square distribution in order to find the p-value. So next thing we're going to do is talk a little bit about a chi-square distribution. The chi-square distribution can be used as long as all of our expected counts are at least 5. If this condition is not met, then we should not be using the chi-square test to do a hypothesis test. Chi-square distributions are a family of distributions. They are also characterized like a t-distribution is by degrees of freedom. The difference here is that the degrees of freedom is not the sample size minus 1. It's the number of categories for a categorical variable minus 1. When we're working with a chi-square distribution to find a p-value, we always use the right tail, and this is because, as I said before, any difference from what we expected to see when the null hypothesis is true is going to create a large value of the test statistic. So it's always going to be the right tail that we use to get the p-value. This slide shows you what chi-square distributions look like for different degrees of freedom. As you can see, chi-square distributions are skewed. They always take on positive values, and they have long tails out to the right. To find p-values with a chi-square distribution, we will use stat key. We'll go to the theoretical chi-square distribution. We'll need to enter degrees of freedom. I'm just going to put in 3 for now. And then to find the areas in the tails, we'll always use a right tail, and we will change the cutoff to be whatever our chi-square test statistic is. And the area in the tail will be given here. So I'm going to summarize the process we use to do a chi-square goodness of fit test, and then we will go through an example. So the first thing we always need to do is state our hypothesized proportions for each category. The alternative is always going to be at least one of the proportions is different than what was specified in the null hypothesis. The next thing we need to do is calculate the expected counts for each cell using n, sample size, times p sub I, and then make sure they're all at least 5 so that we know we can use a chi-square. Next thing we'll need to do is calculate the chi-square test statistic. Once we have the chi-square statistic, we're going to compute the p-value as the area in the tail above the statistic for a chi-square distribution with degrees of freedom equal to the number of categories minus 1. And then the last thing we're going to do is use our p-value to draw a conclusion in context. So here's our example. In Alameda County jury pools, we are going to test to see if the racial distribution of people in the jury pools matches the overall racial distribution of the county as given in the U.S. Census. The values are given in the table. So the data here are the number in the jury pools. We can see that it's broken down by race, white, black, Hispanic, Asian, and other. And the census percentages that occur in the entire county are given down below. So those are what's going to be our hypothesized values in this situation, because we want to see if there's evidence that jury pools are not reflective of those census percentages. So the first thing we need to do is make our hypotheses. And here they are. The proportion white is 0.54. The proportion black among all jurors is 0.18. That the proportion Hispanic among all jurors is 0.12. The proportion Asian is 0.15, and the proportion other are 0.01. And our alternative, again, is that at least one of the proportions is not correctly specified in the null hypothesis. So next we need to calculate the expected counts. So remember that the way we calculate the expected counts is we take the proportion that's hypothesized for each category and multiply by the sample size. So I calculated the total sample size over here, 1,453. And so the expected count for white jurors is going to be 0.54, the hypothesized proportion white, times our total sample size, 1,453, and that gives us an expected count of 784.62. And I repeat this process for the other categories, multiplying the hypothesized proportion by the sample size and calculating an expected count for each of the race categories. Note that all of the expected counts are at least 5, so we can use the chi-square test. So the next thing we want to do is calculate the chi-square test statistic. To do this, for each of the race categories, I'm going to take the observed count minus the expected count, square that, and then divide by the expected. So for the white category, we have an observed count in the jury pool of 780. So put 780. I subtract off my expected count of 784.62. I square that, divide by 784.62, that's our expected count again, and I get this contribution for that category here is 0.0272. And I go through and I do the same calculation. Next time I'll do it for the black category. I'll take the observed minus the expected, square that, divide by the expected, and so on. And if I do that for each category, you can see I have a contribution to the chi-square test statistic for each of the categories. And if you're not sure that you know how to calculate that contribution, why don't you go ahead, stop the video, and try one of them and make sure you come up with the same number. Now, once I have all the contributions there from all the different categories, the chi-square test statistic just requires that I add those all up. So my chi-square test statistic is the sum of those contributions, and I get a value of 357.3624. Now I'm going to need to use StatKey to look up the p-value so I can draw a conclusion and decide whether or not to reject my null hypothesis. To do that, I need to know how many degrees of freedom there are for my chi-square distribution. Remember, the degrees of freedom are the number of categories minus 1. Here we have 5 different race categories, so I'll use 4 degrees of freedom. And again, I'm going to use StatKey to get the p-value. So here in StatKey, I go to the chi-square distribution, and I put in my 4 degrees of freedom. Now my p-value is going to be the area in the right tail beyond my chi-square test statistic. So I click on right tail, and then I'm going to click on the cutoff down at the bottom and change it to my chi-square test statistic. My chi-square test statistic was 357.3624. And that gives me my p-value here of 0. So coming back to our example, we know our test statistic was 357.3624. We used a chi-square distribution with 4 degrees of freedom to find a p-value of 0. That p-value is very, very strong evidence against the null hypothesis, so we'll reject the null hypothesis. And we can conclude that there is strong evidence that the racial distribution of people in the jury pools in Alameda County does not match the overall racial distribution of the county. I hope this video is helpful as you get started using the chi-square goodness of fit test. It's a very useful test in situations in which we're interested in one categorical variable with more than 2 categories. And so that means that there'll end up being more than one proportion that we need to make hypotheses about. Thanks, have a good day.